Hi, my name is Luca Borzacchiello. I'm a PhD student at Sapienza University of Rome, and I'm going to present fuzzing symbolic expressions. The idea of this work is to speed up the solving time, specifically in concolic execution. So let's first recap what symbolic execution and concolic execution is. The goal of symbolic execution is to automatically explore paths in a given program, keeping track of computation in terms of symbolic expressions. So for example, if we want to execute the function f symbolically, we will initialize the variable x with a fresh new symbol. At branches, the execution state is split in order to model the two outcomes of the branch. The branch condition can be divided into two parts: pi, that represents the constraints collected during the execution of the path, while b, that represents the current local branch condition. In the example, since we have executed the first branch of f, pi is initialized with true. Same thing with the other branch, but this time the value of pi is the value of all the branch conditions encountered during the execution of the path, that in the example is only the previous branch condition. Using an SMT solver, we can solve the query pi and b or pi and not b for every branch, getting a concrete assignment for the symbolic variables that drives the concrete execution towards the chosen path. Concolic execution is a twist of symbolic execution where a concrete input that we name the seed drives the execution. So instead of executing all the paths as we do in symbolic execution, in concolic execution we will execute only one single path. Note that the seed is a satisfiable assignment for pi and b for every taken branch condition. To generate an input that satisfies the other outcome of the branch, we can solve using an SMT solver the query pi and not b. Now let's talk about fuzzing, and in particular hybrid fuzzing. The goal of fuzzing is to find bugs in a program. It does that by mutating inputs taken from an input queue, and coverage-guided fuzzers in particular populate this input queue using coverage. That is, a new input is added to the queue only if it exercises new coverage in the program. In hybrid fuzzing, a concolic executor typically reads from the input queue of the fuzzer and generate new inputs that are then written back to this input queue. Now, the key insights for our work are the following. The first one is that given a branch query of a concolic executor, not b and pi, the seed that has driven the concolic expression satisfies by the sign pi, as we have seen in the previous examples. The second insight is that fuzzing transformations has been proven effective in overcoming most of branch conditions. And the last insight is that while SMT solvers are complex and offer a rich set of solving primitives, most concolic executors, such as QSIM, are built only on a few of them. So let's talk about our approximate solver fuzzysat. The idea of our approach is the following. Given a branch query not b and pi and the seed, we will mutate the bytes of the seed trying to solve not b while keeping pi satisfiable. We do that in two stages. The first stage is the analysis stage, where we learn from the symbolic expressions added to pi. The second stage is the reasoning stage, where we use the acquired knowledge from the analysis stage to apply simple but fast transformations to the seed. So let's briefly talk about the analysis stage. Notice that I will omit some details that are, of course, detailed in the paper. So the analysis stage is composed by some phases. The first phase detects input groups. For us, an input group is a group of symbols that are used together in the expression without mixing their bits. So for example, in the first expression of the slide, we have I0 concatenated with I1, and for us this is an input group. The second phase simply collects constants within the symbolic expression. The third phase detects input to state expressions. Here the term input to state is taken from the Red Queen Fuzzer paper, and for us an input to state comparison is a comparison of an input group with raw bytes. The last phase of the analysis stage is the detect range constraints phase, that detect patterns where a constraint set an upper bound or a lower bound to an input group and reduce the constraint to a range. Now let's talk about the reasoning stage, that is the stage that is in charge of actually mutating the bytes in the seed, and it is composed by the mutation engine and the multi-goal engine. Let's talk about the mutation engine, that again is composed by some phases. The first phase is the input to state phase, that simply checks whether a query has been tagged as input to state by the analysis stage and if so, it tries to substitute the raw bytes in the input group. The second phase is the range brute force phase that checks whether a query contains only a single input group and checks whether the analysis stage associated with to this group a small interval, and if so, it tries to brute force all the values of the interval in this input group, trying to solve the query. The third phase is the gradient descent phase, where we try to reduce the query to a minimization problem, and we use the gradient descent algorithm to solve it. The last phase of the mutation engine is inspired by the mutation stages of the AFL fuzzer. So we will apply the AFL transformations, but differently from AFL, our mutations are applied only to the bytes involved in the branch condition, and multi-byte mutations are considered only in the presence of multi-byte input groups. Now, the reasoning engine mutate only the inputs contained in the local current branch condition, but this is too restrictive. If we consider this example, where we have spi I0 equals to I1 and sb I1 equals to 1, as we can see, we cannot solve pi and b mutating only I1, that is the only input that appears in b. So the multi-goal engine employs a greedy approach to solve this problem. So assuming that the reasoning stage solved B, the multi-goal engine checks whether B has conflicting constraints in pi, and if so, it tries to solve the conflicting constraints without modifying the bytes involved in B. Of course, this is an approximation, but we do that in this way to be more scalable and to scale on large queries. Now let's talk about implementation. We implemented fuzzysat as a C library that operates on Z3 expressions, and we integrated this library in the QSIM concolic executor and in Fuzzolic, where Fuzzolic is a new concolic execution and executor based on QEMU and written by us that instrument programs at binary level using TCG. We open sourced both fuzzysat and Fuzzolic, and they are available at the link in the slide. Now let's talk about evaluation. We evaluated our approximate solver fuzzysat against the SMT solver G3 and the approximate solver JFS. We evaluated it on a set of queries generated by QSIM on 12 real-world programs, such as readelf and libpng. And as we can see from the graphs on the right, fuzzysat succeeded in solving more queries overall with respect of both Z3 and JFS, spending significantly less time. As second part of evaluation, we wanted to evaluate how fuzzysat behaves in the context of hybrid fuzzing. So we evaluated Fuzzolic with fuzzysat against 3 state-of-the-art fuzzers and concolic executors. In particular, we evaluated it against AFL with 3 instances, 1 master and 2 slave, AFL++ with 3 instances, 1 master and 2 slaves, and QSIM and Eclipser with 1 master and 1 slave of AFL++ and 1 of their own instances. Fuzzolic, again, is the setup of Fuzzolic is the same, so 1 master and 1 slave of AFL++ and 1 of its own instance. We ran 8-hour experiments on 12 real-world programs, and Fuzzolic succeeded in reaching a higher coverage in 7 out of 12 benchmarks. So this concludes my presentation, so thank you. If you have any question, please ask. And again, we open sourced both the concolic executor Fuzzolic and our approximate solver fuzzysat, and the code and the documentation can be found in the link in the slides. So again, thank you.
Okay, it looks like we are live. Hello, everyone. Welcome to the session on fuzzing. The author, Luca, is with us and can take questions, so please go ahead and use the chat window. Questions for Luca? Okay, maybe they're going to come through. I'll start in that case, Luca. I'm wondering what you do about floating point operations. Do you handle them in any special way or through a workaround?
Actually, we don't handle floating point operations, so neither our fuzzer, neither our fuzzolic, so the concolic executor, can handle floating point operations. But actually, we are planning to work on that. JFS, for example, can solve floating point constraints, so it is possible to implement that in both fuzzolic and maybe fuzzysat.
Okay, thank you. And another question is there some kind of a sweet spot for using fuzzysat? For example, is there a type of concolic executor for which your approach is particularly appropriate?
Well, this is a nice question. Actually, fuzzysat operates mainly only on concolic executors. So I think that whatever concolic executor is okay. The important thing is that you can have a concrete assignment for the constraint that is a satisfiable assignment for pi. If you have that, then you can use fuzzysat. Of course, as we have said, floating point operations are not supported right now. But apart from that, I think that whatever concolic executor should be improved with fuzzysat, or at least used with fuzzysat.
Okay, thank you. We do have a question from Neumeyer. Neumeyer is asking, thanks for the talk. Although your experiments are in the context of concolic execution, is this a constraint? Can you use it on more general SMT queries, given some strategy for concretizing some part of the expression?
It is a constraint in the sense that you must have a concrete assignment to mutate and to solve the query starting from this assignment. But I mean, the assignment can be also all zeros. So of course the performance of the solver will decrease. But this is a constraint in the sense that you must have a concrete assignment that at least is a satisfiable assignment for some parts of the query. But I mean, this is only this will if you use an empty seed or a seed filled with zero, it will only decrease the performance of the solver. But there is, I mean, there is no other reason why the solver cannot be used in other contexts.
Okay. Neumeyer, are you satisfied? Do you have any follow-up questions on that? Okay, maybe since we have time, I have one more question and I don't see anything on the chat window. I'm wondering whether the approach can be combined with like traditional SMT solver, maybe in order to balance like accuracy and time complexity so that you get best of both worlds. By accuracy, I mean giving a solution when it exists and when it's possible to do so without being too expensive.
Absolutely, this is a very nice question, and it's something that we work on it, and we are working on it, and the main goal is to use fuzzysat for some time and then to switch to an SMT solver, because probably later on during a fuzzing session, most of the simple queries that are the ones that can be solved by fuzzysat are solved. So the remaining queries are complex, are to solve, and probably an SMT solver is able to solve them. So I mean, in a hybrid approach where we use fuzzysat for the first part and then an SMT solver, traditional SMT solver, later on during the fuzzing experiment, is absolutely something that can improve the coverage that the fuzzer can find. In particular, in long experiments. I mean, after one day, maybe fuzzysat cannot solve cannot solve the queries that are generated by the concolic executors, because all the simple ones are already being solved.
Okay. Is there a way to gauge whether the problem is easily solvable with some pre-analysis and then dispatch it to SMT solver or fuzzysat, or you have to really first try it, and then if it's not successful, then you go with the other approach?
I mean, the simple solution is to simply try for some time with fuzzysat and then switch. Of course, it's nice thing to do is to switch in a smarter way. I mean, to the SMT solver. I'm probably by using some sort of static analysis. I'm probably with some sort of static analysis on the program, you can decide whether a certain branch can be solved with an SMT solver, because you have some indication that for you it's hard to solve for fuzzysat and can be solved with an SMT solver.
Yeah, that's what I was actually trying to get at.
Yes, absolutely.
All right, I'm not seeing anything else on the chat window. In that case, we have still a few more minutes. I'll let you stay on the stage for the remaining time. And then if people care to join the discussion room, then you will all be taken to the discussion room. The system will ask you, then you can continue offline discussions one-on-one with the people if you wish. Okay. So what I'm going to do is I'm going to leave you here and then go to my next backstage. I just suggest that you stay here for another 2 minutes until the session is over, and then you can decide whether you want to join the discussion room or not, along with some of the audience members.
Okay.
All right. Okay. Thanks a lot, Luca. So let's give a virtual applause to Luca.
Thanks.
And the next paper is going to start in the session, the last paper, in about 2 minutes. Thank you, everyone.